Have you ever stopped to consider what truly organizes the cosmos? We often look up, past the moon, past the familiar planets, searching for the grand answers, but sometimes the most profound secrets hide in plain sight. They are tucked away in the shadows, among the smallest, most unassuming bodies orbiting our Sunday. These aren't the majestic gas giants or the fiery star. They are the leftovers, the cosmic dust motes, and ancient icy travelers. Yet, these tiny worlds hold the fundamental clues to how everything began. How did our solar system coalesce? What unseen forces dictate its delicate, billion-year-old dance? We're going to slow down, look closer, and examine the surprising complexity buried within the simplest structures. It's an exploration into the deep mechanics of space, stripped of the usual drama. If this measured approach to discovery fits your curiosity, a gentle like and subscribe helps us share these insights with others who feel the same way. Settle in. Let's uncover the silent, powerful truths hidden in the solar system's forgotten corners. The year 2011 marked a major shift in our view of the solar system's minor bodies. For over 2 centuries, scientists had known about the giant rocks circulating in the asteroid belt. Most of that time, these objects were nothing more than tiny, distant points of light in a telescope. The very first of these to be found, named Ceres, was discovered in 1801 and was initially added to the list of planets. Just 1 year later, Pallas was found, followed quickly by Juno and then Vesta. Because of these discoveries, by 1845, our solar system officially contained 11 planets. This roster included the original 7 from Mercury, up through Uranus since Neptune had not been located yet, plus these 4 large asteroids. However, as more and more of these orbiting rocks were mapped, it became entirely clear that they could not all be categorized as planets. This distinction proved essential, as today we have tracked millions of asteroids of wildly varying shapes and sizes. Yet, before 2011, humanity had never managed to see any of the original 4 asteroids up close. This is where the Dawn spacecraft entered the story. Launched in 2007, Dawn was given an exceptionally challenging mission: to journey to and thoroughly investigate not just 1, but 2 of these significant early asteroids. Its itinerary involved reaching Vesta first and then moving on to Ceres. The fundamental question for the scientific community was simple: what specific structures and secrets did Dawn uncover during its long-term study of these 2 worlds? To answer this, we must first look at the technology that made the mission possible. Dawn's 4-year cruise toward Vesta involved a gravity assist or slingshot maneuver around Mars from a basic distance. This transit might not seem remarkable, yet a closer look at the Dawn spacecraft itself reveals its profoundly special feature: an ion engine. Ion propulsion had been successfully tested previously on NASA's Deep Space One probe. However, the way Dawn utilized this technology represented a massive step forward. Due to the efficiency of its ion engine, Dawn made history as the first ever spacecraft to enter orbit around two distinct extraterrestrial bodies. The core principle behind ion thrusters is that while they produce very little thrust or pushing force, they are incredibly efficient in their use of propellant. This efficiency allows them to remain operating for much longer periods than traditional chemical rockets. Unlike conventional chemical thrusters, which rely on powerful, hot, high-pressure reactions to push gas rapidly out of the back of the rocket, ion thrusters operate differently. They simply use electricity to ionize neutral xenon gas, meaning they strip electrons from the gas atoms, creating a charge. These charged particles are then accelerated and rushed out of the engine at a speed of 150,000 kilometers per hour, or 93,000 miles per hour, which pushes the spacecraft gently in the opposite direction. Because the ionized gas is expended so slowly, the acceleration produced by Dawn's engine is extremely gradual. To put this into perspective, it would take Dawn a full 4 days to accelerate from a complete stop to 100 kilometers per hour, or 62 miles per hour. But over the extended time frame of deep space travel, these small, constant pushes add up significantly. Dawn kept its thrusters firing for 85% of its travel time during the journey to Mars. In doing so, it used just 72 kilograms, or 159 pounds, of its xenon propellant, while gaining a total velocity increase of over 1.8 kilometers per second. Upon finally reaching Vesta in July 2011, the images that Dawn began transmitting back to Earth genuinely astonished the global science community. What they saw was definitely not what they had expected. Once Dawn was successfully captured by Vesta's gravity, it gradually lowered its orbit to begin a much closer examination of this unique asteroid. So, what exactly made Vesta such an unexpected and delightful surprise? The first striking characteristic one notices about Vesta is its irregular, slightly squashed appearance. It does not possess a perfectly round shape. There are two primary reasons for this distinct form. The first reason is that Vesta is simply not large enough. Though it is huge compared to most other asteroids, it remains quite small on a full astronomical scale. Vesta is not quite massive enough to achieve what scientists call hydrostatic equilibrium. This complex term simply means that the object's own gravity is not strong enough to pull all of its material into a perfectly round, spherical shape. Vesta's diameter measures approximately 500 kilometers, or 310 miles. Its surface area is roughly 800,000 square kilometers, or 310,000 square miles, which is comparable to the size of Pakistan. To fully appreciate its small scale, it helps to compare it to our own moon. Despite its relatively small size, Vesta still accounts for about 9% of the total combined mass of the entire asteroid belt. This fact helps illustrate just how widely and thinly the material of the asteroid belt is spread out across space. The second reason for Vesta's unique, irregular shape lies in two massive impacts it suffered long ago. Scientists estimate that over 1 billion years ago, Vesta was struck not once, but twice near its south pole by objects that were themselves planetary in scale. These colossal collisions were so powerful that the resulting craters penetrated all the way through Vesta's outer crust and down into its mantle. Over the eons, the outer crust has cooled off and solidified, leaving behind a vast, complex crater structure called Resilvia. Because the two impact sites overlapped, Resilvia is the most recent and therefore the most visible and prominent crater remaining today. As is typical for large, complex craters, large stepped walls, known as terrace walls, can be observed around the edge of the impact site. These take the form of huge, deep troughs wrapped around Vesta's equator, structures that dwarf the scale of Earth's Grand Canyon. Another common feature of complex craters is a distinct, prominent central peak. This immense central peak was once hypothesized to be the tallest mountain in the entire solar system. However, more precise observations gathered by the Dawn mission confirmed that the title rightly belongs to Olympus Mons on Mars. Nevertheless, the peak inside Resilvia is still extraordinarily tall, rising between 20 and 25 kilometers, or 12.5 to 15.5 miles, and stretching over 100 kilometers, or 62 miles, across. Given its size relative to the overall size of Vesta itself, the structure appears from orbit almost like a gigantic protrusion on the South Pole, making it easily visible. The two violent collisions that sculpted Vesta's South Pole ejected an enormous amount of material into space. So much debris was flung into the asteroid belt that the resulting space rocks have been assigned their own distinct asteroid spectral classification, known as V-type asteroids. Scientists believe that V-type asteroids overwhelmingly originated from Vesta, and many of them can be directly traced back to the energy of those specific impacts. But these fragments did not just remain confined within the asteroid belt. They were scattered across the whole solar system. In fact, roughly 5% of all meteorites that eventually land on Earth have been identified as originating from Vesta. These rocks are specifically categorized as Howardite-Euclid Diogenite, or HED, meteorites. This fact is extremely convenient for researchers, as it means we never needed to launch a dedicated sample return mission to bring pieces of Vesta back to the lab. Vesta has already delivered its own samples directly to our planet's front door. The composition and structure of these terrestrial meteorites offer crucial clues about how Vesta originally formed, and the Dawn mission worked to deepen that understanding with direct observations. Combining all the data collected, scientists have confirmed that Vesta is truly a unique body in our solar system. It is considered the only remaining rocky protoplanet, or in simpler terms, it is a planetary embryo that simply never finished the job of forming into a full planet. The currently accepted theory suggests that as the solar system took shape, dust and gas from the early protoplanetary disk gathered together, or coalesced, into thousands of separate planetary predecessors called planetesimals. These planetesimals continuously collided with each other over massive stretches of time, gradually building up the large, stable planets we observe today. Even our own moon is believed to have formed from one such impact, specifically a collision between Earth and a large, theorized planetesimal named Theia. The debris generated by that colossal crash slowly gathered together, or coalesced, in Earth's orbit, and, over time, rounded under its own gravity to form the moon we recognize today. Vesta clearly began its own journey toward becoming a planet. It experienced many significant impacts with these large planetesimals. As a direct result of the energy generated by these collisions, the intense heat meant that at one point in its history, Vesta possessed an active mantle beneath its surface. Even today, scientists believe that Vesta still contains a dense, metallic core of iron, measuring about 220 kilometers or 137 miles in diameter. This core is structurally similar to the cores found in other terrestrial worlds like Mercury, Venus, Earth, and Mars. However, Vesta's interior has long since cooled off, meaning the interior layers have solidified. If not for the two massive collisions we discussed earlier, this differentiated internal structure possessing distinct layers like a core and mantle would likely qualify it as a dwarf planet today. One of the main criteria for a dwarf planet is that its mass is sufficient to pull its body into a round shape through its own gravity. Because the two devastating collisions happened roughly 1 billion years ago, which was several billion years after Vesta first formed, the body had already cooled too much. This meant Vesta was no longer sufficiently elastic or flexible to return to a shape that satisfied hydrostatic equilibrium. As for why Vesta never truly grew into a full planet, scientists are currently pointing the finger at the largest player in the neighborhood, Jupiter. The gravitational forces exerted by Jupiter are theorized to have either stolen mass that would otherwise have been incorporated into Vesta, or disturbed enough of that crucial material to permanently prevent Vesta from ever getting its full development underway. To the unaided human eye, Vesta appears rather ordinary. The true color images we receive show a body that seems mostly bland. However, when using specialized cameras capable of sensing a wide range of light wavelengths, Vesta's astonishing variety suddenly becomes clear. In composite images, for example, the material that appears black is believed to be debris thrown out by a large meteorite impact. The material that shows up as red is also likely the result of an impact, but consists of matter that was subjected to intense heat, melting before cooling and solidifying once more. The Dawn mission also delivered some completely unexpected findings right on Vesta's surface. Vesta was generally considered to be an extremely dry body, containing little to no volatile substances like water or frozen gases in its crust. If this is true, then why did Dawn observe distinct evidence of past liquid flow? In one specialized false color image, you can clearly see a crater measuring a couple of kilometers across, with a clear channel flowing out from it. The different colors in the image indicate that this channel material is made of a different substance than the surrounding terrain. The precise origin of this flow material remains an open question, but one possibility is that it was brought by the impacting object itself and melted upon collision with Vesta's surface. Another remarkable discovery was made within one of Vesta's younger craters, named Marcia. Near the bottom of this crater, Dawn captured images of what scientists refer to as pitted terrain. The existence of pitted terrain on Vesta is something of a mystery, as it had only ever been observed on Mars prior to this discovery. However, the leading scientific explanation is that rocks on Vesta's surface containing hydrated minerals meaning they have water chemically locked inside their structure, were rapidly heated, perhaps by a subsequent impact. This intense heat released the trapped water, which immediately and violently expanded or degassed into the vacuum of space. This explosion of vaporizing water left behind the distinct small craters we now see. It is worth noting that this Marcia crater is part of a larger chain of craters that forms the famous shape on Vesta, known colloquially as the snowman. What is particularly interesting about this region is how relatively smooth the terrain is surrounding the craters. Scientists believe this smoothness exists because a thick ejecta blanket, a layer of material thrown out by the initial impacts, covered the entire area, effectively smoothing over the older, rougher features. Dawn's mission around Vesta lasted for only 1 year before the spacecraft left Vesta's orbit and began the second phase of its historic journey, heading toward the actual dwarf planet, Ceres. Utilizing its highly efficient ion engine, Dawn was able to continuously build up velocity until it was finally fast enough to overcome Vesta's gravitational pull completely, allowing it to start its long cruise towards Ceres. The sense of anticipation and excitement within the scientific community to finally reach Ceres was intense and easy to feel. Even with the assistance of the powerful Hubble Space Telescope, the best image we had of Ceres before Dawn arrived looked like a simple, blurry sphere. It was still very much a mysterious body. What complex structures or materials were waiting for us there? Would the aging Dawn probe hold up after years spent traveling through the harsh environment of space? And perhaps most importantly, what would Ceres reveal about the deepest secrets of our own solar system's past? After 2 full years in transit between the two worlds, Dawn finally began its approach to Ceres. As the days passed, the resolution of the images returned by the spacecraft improved dramatically. Surface details, specifically large craters, could finally be resolved. And most intriguing of all, distinct bright white dots began to appear. At the time these early, low-resolution images were arriving, speculation was widespread about the identity and nature of these spots. As higher resolution images were received, the bright spot initially looked like 2 separate patches. Then, even greater resolution revealed that it was, in fact, several different spots clustered together. Dawn also observed the heavily scarred appearance of Ceres up close, with many craters marking the surface. Interestingly, however, the number of large craters was not as high as scientists had predicted. Considering this relatively lower crater count, combined with the presence of the bright spots, it became clear that Ceres is not nearly as inactive or inert as we might have previously assumed. Before we dive deeper into the implications of these observations, we should establish some context. Ceres is an extremely unusual body, almost seeming out of place within the asteroid belt. Most other asteroids are primarily composed of non-volatile substances, meaning rocks and metals. Ceres, by contrast, has a composition that strongly resembles that of a comet. It is, in essence, a world built largely of ice. However, being so close to the Sun, any ice that might appear directly on Ceres' surface rapidly sublimates. This means the ice turns straight into a gas, bypassing the liquid phase. For this reason, the very top layer, or crust, of Ceres is believed to be rocky yet porous, with water ice locked into the gaps beneath the surface. Scientists estimate this upper layer contains a ratio of roughly 90% rock and 10% water ice. Beneath this porous crust, there is thought to be a muddy, deep mantle layer and an interior core composed of hydrated rocks, such as clays. In these lower regions, rock and brine, a mixture of water and salt, are potentially mixed together at a 50-50 ratio, though this composition has been challenging to confirm definitively. Some alternative models suggest that the core might be much drier and smaller, with a greater volume of water ice concentrated within the mantle. Regardless of the exact internal structure, water is absolutely present in Ceres in very large quantities. Its low overall density suggests that water ice could constitute as much as 50% of its total volume. And it is this massive amount of water that is believed to slowly renew Ceres' surface, although this renewal process occurs over immensely long timescales. These enigmatic bright spots are now understood to be the result of a phenomenon known as cryovolcanoes. Unlike typical volcanoes, which erupt molten rock or lava from the mantle, cryovolcanoes erupt water and other volatile substances. The largest bright spot observed on Ceres, known as Spot 5, has been modeled in 3 dimensions using Dawn's data. The water on Ceres is extremely rich in salt. This means that when a cryovolcano on Ceres erupts, the water released rapidly sublimates into space, leaving the salt crystals behind on the surface. This process was directly observed over the brightest region, Spot 5, where a haze was periodically seen above the area. This haze strongly indicated that water was actively sublimating or vaporizing from that location. These bright, salty patches gradually darken over vast stretches of time due to space weathering, which is the erosion caused by constant exposure to the sun's radiation and micrometeorite impacts. Therefore, it is highly likely that many old, now darkened cryovolcanoes exist across Ceres' surface, and we are only able to observe the most recently active and brightest ones today. The astonishing discovery of the bright spots was certainly not the end of the evidence regarding active water on Ceres. In fact, numerous other clusters of these highly reflective areas are dotted across the dwarf planet's surface, not just confined to the famous Ocata crater. Furthermore, water was identified in entirely different, more static regions of Ceres as well. This finding is due to a simple but crucial orbital mechanic. Ceres has a very minimal axial tilt. It leans only about 4 degrees relative to its orbit. Because of this slight tilt, some of the deepest craters located near its poles remain in a state of perpetual darkness. The crater floors in these areas never, under any circumstances, receive direct solar radiation. This permanent shadowing is critical because it means that fragile water ice can remain stable there indefinitely, never sublimating or turning directly into a gas. This mechanism is strikingly similar to what scientists hypothesize occurs on our own moon, where thick deposits of water ice are thought to have been trapped at the bottom of permanently shadowed craters for billions of years, offering a potential resource for future human missions. Beyond the water-related features, what other distinct surface characteristics did the groundbreaking Dawn spacecraft document on Ceres. As we've noted, it photographed an abundance of craters, each displaying unique and complex characteristics that speak to Ceres's violent past and ongoing geological processes. Some impact sites appeared remarkably round and sharply defined, suggesting they were relatively fresh or that the material was uniform upon impact. Others showed long scars or cracks running along the crater floor, indicating internal stress or movement after the impact. There are plentiful examples of complex craters featuring the tall, distinctive peaks right in their centers, peaks that rebounded upward after the immense pressure of the initial collision. Dawn even meticulously documented direct evidence of crater rims collapsing. Large, fractured rocks were clearly photographed having broken away and fallen from the steep, unstable inner walls of the craters. Even smaller geological activity was captured. Tiny rocks were spotted having tumbled down crater slopes, leaving telltale trails etched into the fine material below. These small signs of movement emphasize that Ceres, though cold, is still a dynamic environment, subject to gravity and internal shifts. The images taken at an oblique angle, deliberately pointed along the limb or the edge of the dwarf planet, are particularly valuable for visual understanding. To the viewer, these photographs provide a much better, more three-dimensional sense of the vertical scale and depth of the features we are examining. However, it is important to remember a key visual challenge in space photography. Without a thick, scattering atmosphere to provide natural shadows and haze, it can still be quite difficult to accurately judge the true height and size of features just by looking at these flat images. In addition to impact features, numerous extensive fractures were systematically documented all across Ceres' surface. These cracks and lines indicate that the rigid, icy crust has been subjected to significant internal stress and pulling forces over vast stretches of time. Scientists have been able to date some of these fissures as relatively young, perhaps forming only a few 100 million years ago, which is recent in the life of the solar system. Some of these stress features manifest as long grooves and troughs, representing regions where the crust has been pulled apart and stretched thin by internal expansion. Conversely, other fractures are visible as pronounced rows of mountains or ridges, which form where the crust has been forcefully compressed and pushed together. One feature, in particular, stands out as a singular, perplexing mystery, a mountain known as Ahuna Mons. It is truly an isolated structure, standing about 20 kilometers wide at its base and towering 5 kilometers high. The truly strange thing about this mountain is that it simply projects straight up from the surrounding, mostly flat, plain, without any readily apparent geological cause or connected mountain range. If there were other mountains of this type scattered across Ceres, it might be interpreted as evidence of a global process, perhaps a past system of plate tectonics. But Ahuna Mons is unique. It is the only feature of its kind on the entire world. This makes finding its true origin much harder. The most compelling current scientific hypothesis suggests that Ahuna Mons is an ancient cryovolcano, but one formed under highly unusual circumstances. It is theorized to be a consequence of a major impact that occurred directly on the opposite side of the dwarf planet. When a large celestial body strikes, the immense energy generates powerful seismic waves that travel deep through the world's interior. The specific point on the surface that is exactly opposite the impact site is known as the antipode. This is where the seismic waves converge again, potentially causing geological chaos. Antipodal regions are often centers of strange terrain across the solar system. We see examples of this chaotic deformation on Mercury and other bodies. Ahuna Mons appears to fit this description perfectly. Scientists theorize that the powerful, focused energy of the seismic waves from an impact on the far side of Ceres effectively triggered a powerful, localized, cryovolcanic eruption at this antipodal point. This eruption would have slowly extruded cold, salty water and mud, a thick cryomagma which froze in the vacuum of space to build the solitary dome structure we see today. If Ahuna Mons is confirmed as a cryovolcano, it would be structurally classified as a dome volcano, resembling terrestrial examples like Mount Street, Helens, or certain large dome features previously observed on the surface of Mars, further linking the small worlds of the asteroid belt to the processes that shape the terrestrial planets. The pioneering and incredibly successful Dawn mission officially came to its end in October 2018. The spacecraft had finally exhausted its critical supply of xenon propellant. Without this inert gas, the probe could no longer power its ion engine to precisely adjust its position. This meant the spacecraft lost the ability to keep its antennae accurately pointed toward Earth, to transmit its invaluable data, or to receive new operational commands. Dawn was automatically shut down and has been left in a perfectly stable, permanently deactivated orbit around Ceres. It now orbits as an enduring, silent monument in space, one that planetary scientists estimate will remain captured by Ceres's gravity for at least another 20 years. The truly revolutionary data and the vast catalogue of discoveries made by the Dawn mission will continue to form the essential foundation of asteroid and dwarf planet research for many generations of scientists to come, guiding our understanding of how our solar system truly formed and evolved. The end of the Dawn mission in 2018, while marking a significant achievement, also left behind an important legacy that goes beyond its data. The ion engines were the singular key to its monumental success, enabling it to travel to and orbit two separate major solar system bodies. Today, numerous other space missions rely on this technology. For instance, the Starlink satellites, operated by SpaceX, utilize ion thrusters to maintain their precise orbits. Similarly, the Tiangong space station being constructed by China uses them for orbital maneuvering. Looking ahead, the European Space Agency's Bepi-Colombo mission is using ion propulsion for its complex journey to the planet Mercury. Even NASA's upcoming DART mission, which is designed to impact and test deflecting the binary asteroid system of Didymos and Dimorphos, employs ion engines for its long-range transit. Now, we must leave the familiar territory of the inner solar system and the busy traffic of the asteroid belt behind us. In the dim, frigid void far beyond the orbit of Neptune lies a massive and mysterious region. This is where the ancient remnants of our solar system's birth silently drift. They are perfectly preserved, frozen in time by the deep cold of space. To successfully reach this shadowy expanse from Earth, Our journey takes us far past the rocky planets, flying by Mars and then navigating beyond the swirling, colossal storms of the gas giants Jupiter and Saturn. We must continue even farther, past the blue ice giants, Uranus and Neptune, before we finally arrive at our destination. Welcome to the Kuiper Belt. This is a vast ring of icy debris that encircles our solar system, much like a thick, frozen halo. This region is not merely a collection of distant, random space rocks. It is a true time capsule, a pristine record from 4.6 billion years ago, holding the untouched, primordial building blocks of our entire cosmic neighborhood. The Kuiper Belt is home to several well-known dwarf planets and many other mysterious objects that have caused many astronomers to scratch their heads in wonder and confusion. We are going to slow down and explore these worlds that lurk in the permanent shadows of our solar system, piecing together the vital clues they hold about our history, the formation of all the planets, the nature of comet activity, and possibly even the origins of life itself. Before scientists knew for certain that the Kuiper Belt was real, astronomers had long suspected that some vast structure must exist beyond Neptune. For many decades, the public's favorite dwarf planet, Pluto, was mistakenly thought to be an isolated object, drifting alone in the extreme outer solar system. But something did not quite add up. Pluto's relatively small size and, critically, its unusual, highly tilted orbit strongly suggested that it was not an independent, solitary world. Instead, it was likely just one of many yet to be discovered distant objects. In 1951, the Dutch-American astronomer Gerard Kuiper formally predicted the existence of a wide belt of icy objects situated just outside Neptune's orbit. However, telescopes at the time were simply not powerful enough to reliably detect these extremely faint objects at such immense distances, and so the idea remained purely theoretical for decades. That critical situation changed in 1992. Astronomers David Jewett and Jane Liu made the discovery that confirmed the theory. They found the first confirmed Kuiper Belt object, or KBO, which they designated 1992 QB1. It is important to remember that Pluto and its large moon Charon were both discovered before 1992. QB1, Pluto in 1930, and Charon in 1978. But those two objects were only confirmed to be part of the KBO population after the discovery of the 1992 KBO. Since that landmark discovery, thousands more Kuiper Belt objects have been identified and catalogued, truly populating this remote region that lies far beyond Neptune. To truly grasp the immense scale and the precise position of the Kuiper Belt, let's take an imaginative journey in a spaceship, beginning at the Sun and traveling outwards toward the far edge of our solar system. As we proceed, we will compare the Kuiper Belt with both the much more well-known asteroid belt and the far less known Oort cloud. Starting near the Sun, we quickly zip past the four small rocky planets: Mercury, Venus, Earth, and Mars. Between the orbits of Mars and Jupiter, we encounter the asteroid belt. This belt is primarily made up of the rocky, leftover materials from the period when our inner planets were forming. It appears as a thin, widely spread ring of mostly rocky debris. The asteroid belt stretches from about 2.2 to 3.2 astronomical units away from the Sun, and it is approximately 1 astronomical unit wide. As a reminder, 1 astronomical unit, or number, text AU number, is defined as the average distance from the Sun to the Earth. Most of the known asteroids reside within this part of our solar system, and they range dramatically in size. The largest asteroid, Vesta, which we just discussed, is approximately 525 kilometers wide. To give a sense of scale, that width is almost the distance from the city of London to the city of Belfast. The smallest objects are merely tens of kilometers across. However, despite being spread across such a huge volume of space, the total mass of all the asteroids in the entire asteroid belt combined is only about 3% of the mass of our own moon. Moving beyond the asteroid belt, we next encounter the massive gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. These are colossal, massive worlds that utterly dominate the outer solar system. Finally, as we pass beyond Neptune's orbit, which circles the Sun at roughly 30 astronomical units, we reach our true destination, an even more remote and icy frontier, the Kuiper Belt. This vast expanse officially stretches from 30 to 50 astronomical units from the Sunday. It is home to a wide range of intriguing objects, from frozen relics of the very early solar system to several major dwarf planets, including Pluto, Haumea, Eris, and Makemake. Countless other smaller objects, similar to the debris found in the asteroid belt, also reside here. The Kuiper Belt is essentially a gigantic repository of ancient debris left over from the formation of our solar system. In fact, Kuiper Belt objects are considered some of the oldest, most untouched, surviving pieces of the original solar nebula that first condensed to form the planets of our solar system. At one time, in the very distant past, these stray pieces might have had the chance to come together to form yet another planetary body. However, the immense gravitational influence of Neptune prevented these icy objects from properly gathering or coalescing. Neptune's gravity constantly disturbed their orbits, never allowing them to settle and form something new and large. A key difference between the two belts is their composition. Unlike the asteroid belt, which is predominantly made of rocky material and metals, the Kuiper Belt consists mostly of frozen compounds, methane, ammonia, and water ice. This forms a thick, frozen, donut-shaped ring of debris. The Kuiper Belt is estimated to contain hundreds of thousands of large icy bodies, each bigger than 100 kilometers across, and likely more than 1 trillion comets, not counting the smaller dust and debris. The average distance between objects within the Kuiper Belt is so enormous that it can be genuinely hard to visualize. Each of those objects is, on average, spaced between 0.02 to 0.1 astronomical unit apart. To make that more tangible, imagine a separation of up to 10 million kilometers between neighboring objects. Here, in the dim, outermost reaches of our solar system, These icy bodies drift in near silence, perfectly preserving vital clues about the earliest origins of planets and comets. But the exploration does not stop at the defined boundary of the main Kuiper Belt region. Overlapping the outer edge of this main area is another distinct region of the Kuiper Belt known as the scattered disk. This area continues stretching outward to nearly 1,000 astronomical units, with some of its Kuiper Belt objects, or KBOs, possessing highly elongated orbits that take them even farther beyond that mark. Therefore, while the asteroid belt and the Kuiper Belt share some basic similarities as rings of debris, the Kuiper Belt is clearly and vastly more expansive than the inner belt. And while we have reached the furthest edges of the Kuiper Belt, our journey through the solar system's structures is still not complete. There is one other massive structure that completely surrounds every single object and belt we have mentioned so far. This structure is the Oort cloud, a colossal theorized sphere of orbiting icy debris that completely encircles our entire solar system. It is so unbelievably far away that even our most powerful telescopes cannot catch a definitive glimpse of it. So, how do these two gigantic structures, the Kuiper Belt and the Oort cloud, fundamentally differ from each other? For one, the Kuiper Belt is thousands of times closer to the Sun than the center of the Oort cloud. The Oort cloud is theorized to begin at about 2,000 astronomical units and stretch outwards to an incredible 100,000 astronomical units from the Sunday. Another crucial difference is their shape. The Kuiper Belt is a relatively flattened, donut-shaped ring, extending mainly in the plane of the planets, while the Oort cloud is a spherical structure resembling a gigantic, orbiting bubble of swarming icy debris that encompasses the entire solar system from all directions. However, these two structures do share one extremely important function. They are both the primary sources of the celestial phenomenon that we know as comets. The distant Oort cloud is believed to be the source of most long-period comets, which take more than 200 years to complete one orbit around the Sunday. Conversely, the much closer Kuiper Belt is where most short-period comets are born, those that take less than 200 years to complete their solar journey. While the Kuiper Belt remains one of the most massive structures in our solar system today, it represents only a small fraction of what it originally was. Scientists estimate that, combined, the primordial Kuiper Belt likely contained 7 to 10 times the mass of Earth. Over the billions of years of the solar system's history, the shifting, complex orbits of the 4 giant gas and ice planets, Jupiter, Saturn, Uranus, and Neptune, cause most of that material to be gravitationally scattered and permanently lost to interstellar space. What remains today is no more than about 10% of Earth's total mass. Not only has the Kuiper Belt lost the majority of its original material, but it continues to slowly erode away even now. As objects within the belt occasionally collide and break apart, they leave behind smaller fragments in their wake. Some of the resulting fine dust is then gradually pushed or blown out of the solar system entirely by the constant pressure of the solar wind. Sometimes, these collisions, or the powerful gravitational influence of Neptune, will perturb the orbits of Kuiper Belt objects, causing them to head on a new trajectory that dips inward toward the Sunday. These objects become what we classify as short-period comets, which are defined as having orbital periods of less than 200 years. Over time, as these comets approach the Sun, the intense solar radiation causes them to shed material water ice, methane, and dust, producing the spectacular tails of gas and dust we observe from Earth. Several very famous comets originate from the Kuiper belt, or its dynamic extension, the scattered disk. This list includes Halley's Comet, which has an average orbital period of approximately 76 Earth years. Another notable example is Comet Shoemaker-Levy 9, which famously broke apart and violently smashed into the planet Jupiter in 1994. That event was the first ever observed collision between two major solar system bodies. As we know, Jupiter, being immense, easily survived the impact, but the scars left behind were visible even from Earth, creating a truly spectacular, temporary sight. You may have heard recent news about a near-Earth asteroid, possibly designated 2024. Why 4? While there is an extremely small chance of such an object colliding with our Moon, and an even smaller chance of it impacting Earth, the short-period comets originating from the Kuiper belt pose no immediate threat to us within the next 100 years or more. Simply put, this is not something that requires current concern. Despite the fact that the Kuiper belt is now only a small remnant of its former self, it still offers a nearly endless frontier of objects for us to continue exploring. Unlike the mysterious Oort cloud, which we have not yet been able to visit with a spacecraft, we have, in fact, traveled directly to the Kuiper belt. While most of what we know about the belt comes from observations made by ground-based telescopes and the orbiting Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have actually reached this remote region. The New Horizons probe first performed a flyby of the dwarf planet Pluto in 2015, which we will discuss shortly, but it continued its journey deeper into the belt. It then performed a second, historic flyby of a small Kuiper belt object designated 2014 MU69, which was later officially named Arakoth. The name Arakoth means sky in the Native American Powhatan or Algonquian language. This flyby of Arakoth, which occurred in 2019, was the most distant flyby in the entire history of space exploration. It took place approximately 1.5 billion kilometers beyond Pluto's orbit. The New Horizons spacecraft successfully flew as close as about 3,500 kilometers above the object's surface. Even among the complex swarm of mysterious objects that constitute the Kuiper belt, Arakoth managed to completely surprise the New Horizons mission team. Its truly strange shape was unlike anything humanity had ever seen before in our solar system. Arakoth is a small, icy KBO that scientists classify as a contact binary. This means it is composed of two distinct, separately formed lobes that, at some point, merged physically into a single body. Its complete, flattened shape resembles a highly irregular, pancake snowman. Arakoth is just 35 kilometers long, 20 kilometers wide, and only 10 kilometers thick. You might assume there is little fundamental knowledge to gain from such a relatively tiny object. However, What Arrokoth lacked in a proper atmosphere or diverse surface geology, it more than compensated for with its utterly unique structure. The bizarre pancake snowman shape of this Kuiper Belt object provided scientists with crucial insights into the precise mechanism of how the solar system's original planetary building blocks first came together, and how the planets themselves may have formed. Arrokoth's structure seemed to dictate a counterintuitive gravity field and rotation pattern. Several scientific papers published since the flyby have led to what is now considered an almost undeniable truth regarding how planetesimals, the objects that eventually build planets, form. This conclusion was a major, unexpected result for the New Horizons team. Planetesimals are the fundamental structures that form when many smaller objects gently come together to create a larger body, which may eventually combine with others to create a full planet. Until the observations of Arrokoth, there were two competing scientific theories for this initial formation stage. The first was hierarchical accretion, which proposed that small objects would continuously crash into each other at very high speeds until they created something larger. The second was local cloud collapse, which proposed the exact opposite, that nearby objects would slowly, gently come together due to their mutual gravitational attraction, thereby gradually forming larger and larger bodies over time. Now, thanks directly to the Arrokoth flyby and the intensive research into the object's geology, geophysics, composition, and formation, scientists can be relatively certain that the theory of local cloud collapse is correct. The object's remarkably smooth surface and the almost complete lack of internal fractures or stress lines confirm that this cosmic snowman formed when its two component parts came together at an extremely low speed, gently merging rather than violently colliding. Dr. Alan Stern, a planetary scientist and the leader for the New Horizons mission, stated publicly that the evidence gathered was so strong that they had decisively solved a multi-decade debate about how planetesimals form. Thanks to New Horizons, we also received our first truly detailed look at the most famous Kuiper Belt object of all, the dwarf planet Pluto. The spacecraft performed its primary flyby in 2015, allowing us to get up close and personal like never before, capturing those stunning, high-resolution images. The mission collected detailed observations of Pluto and its largest moon, Charon, and was also able to gather data on Pluto's 4 smaller satellites, Nix, Hydra, Kerberos, and Styx. Of course, nearly everyone has seen the stunning, iconic photographs of Pluto's heart-shaped surface region, formerly known as Tombao Regio. But did you know that this famous heart-shaped feature is actually a gigantic glacier, the western lobe of the heart, which is named Sputnik Planitia after Earth's first artificial satellite? Sputnik 1 is a vast glacier made primarily of nitrogen ice that stretches 1,000 kilometers wide and is estimated to be up to 4 kilometers deep in places. It is undoubtedly the largest known glacier in the entire solar system. The eastern lobe of the heart gets its distinct lighter color from nitrogen that is carried or deposited from Sputnik Planitia and settles there as fresh ice. Not only did we receive these stunning visual images of Pluto, but the comprehensive data collected by New Horizons permanently changed how we understand our favorite dwarf planet. It revealed that Pluto is far more geologically complex than previously believed, and offered significant clues to the origin of its famous heart-shaped feature. The initial data led some scientists to believe that Pluto's heart-shaped region could be explained by the presence of a deep, internal water-ice ocean beneath its surface. However, a more recent study, led by astrophysicist Harry Valentine from the University of Bern, has revealed another, perhaps more likely explanation. The heart shape may have been caused by a low-velocity impact that left a gigantic, elongated splatter across the surface of Pluto, specifically creating the western half of the heart shape. This impact would have had to come in at an oblique angle, meaning it did not strike straight on. To visualize this, imagine throwing a water balloon across dry pavement in the same manner you might try to skip a flat stone across a pond. When the balloon scrapes the pavement, it pops, leaving an elongated, stretched-out splat of water across the surface. This kind of angled, low-velocity impact is thought to be very similar to the mechanism by which the western lobe of Pluto's heart feature may have been created. But it wasn't just Pluto itself that offered stunning insights. The images captured of Pluto's largest moon, Charon, were equally incredible. One of the most prominent features visible is an enormous, cracked tectonic belt that stretches across Charon's equator. The very existence and appearance of this feature strongly suggests the presence of a long-gone, subsurface water-ice ocean on Charon. This evidence indicates that in its distant past, Charon possessed enough internal heat to keep a layer of water liquid beneath its icy crust. When that ocean eventually froze, the expansion of the ice caused the crust above it to crack, forming the wide equatorial belt we see today. So, what is the next step in our ongoing quest to fully understand the Kuiper Belt and, consequently, our entire solar system? The pioneering New Horizons spacecraft is expected to finally exit the defined Kuiper Belt region sometime between 2028 and 2029. While there is currently no official target for a further flyby, it remains possible that NASA could identify another suitable object for the probe to encounter before its mission officially ends. New tools, such as the powerful James Webb Space Telescope, the successor to the Hubble, could greatly assist scientists in further analyzing the precise composition of Kuiper Belt objects from Earth's orbit. Looking far into the future, perhaps a robotic mission will eventually allow us to successfully land on one of these mysterious, icy objects, or even collect a physical sample for a return mission back to Earth. Who knows what else we will discover out there in this vast, frozen frontier? As space technology inevitably advances, future missions will hopefully be able to push even deeper into the Kuiper Belt, slowly revealing more of its long-held secrets, one icy world at a time. What if we told you that there is a truly colossal structure that begins right at the very edge of our known solar system, one that completely encircles our sun and all of the planets in a gigantic bubble, and yet humanity has never actually seen it? This structure is theorized to be a vast shell made up of billions, perhaps even trillions, of ancient icy chunks, many the size of mountains, marking what we believe to be the outermost boundary of the solar system. Or, at least, that is what the leading theory suggests. The Oort cloud is an area that is so jaw-droppingly far away that it is beyond the reliable reach of even our most powerful telescopes. It is a region shrouded in deep mystery and intense speculation, where the sun's gravitational influence grows incredibly faint as it finally brushes up against the total void of interstellar space. What exactly is this cloud? If we have never directly observed it, how do we know it is likely out there? And why do some scientists still question its precise existence or boundaries? We are going to venture to the farthest reaches of our solar system and beyond, attempting to construct a clear image of this unseen astronomical wonder. You have likely heard of the asteroid belt, and now you are more familiar with the Kuiper belt. Located at two different positions in our solar system, both of these are roughly donut-shaped bands of debris. Crucially, the objects in both belts move in the same general direction and mostly within the same orbital plane as the planets around our Sunday. The asteroid belt is the closer of the two to the Sun, situated between Mars and Jupiter, and consists of millions of orbiting rocky asteroids. The Kuiper belt, on the other hand, was first formally proposed by astronomer Gerard Kuiper in the mid-20th century as the origin point for short-period comets. It is a massive, widely spread field of icy debris that lies far out past Neptune. Occasionally, a piece of this Kuiper belt debris will have its orbit disturbed or pushed by gravity, sending it onto a new trajectory that takes it closer to the Sunday. In many cases, this disturbance creates a new short-period comet. These comets are defined by having orbital periods of less than 200 years and are often predictable because they continue to make subsequent, regular orbits around the Sunday. At the exact same time that Kuiper was investigating the origins of short-period comets, a Dutch astronomer named Jan Oort was contemplating the origin of long-period comets. Few scientists of the 20th century made more fundamental contributions to astronomy than Oort. In 1927, he accurately calculated our position within the vast Milky Way galaxy. In 1932, he was the first to find compelling evidence suggesting the existence of dark matter, to name just two examples of his pioneering discoveries. In 1950, Oort was the first to definitively theorize the existence of a thick, spherical bubble of swarming icy debris that completely surrounds our entire solar system. This hypothesized structure is now universally known as the Oort cloud. But unlike the asteroid belt and the Kuiper belt, the Oort cloud remains to be directly observed by humanity. To understand why this theory was necessary, we must look at the evidence that led Oort to his proposition. Unlike comets with short, predictable orbits, such as Halley's Comet, with an average period of about 75.3 years, or Comet Encke, which has a period of just 3.3 years, the long-period comets were completely unpredictable. For one thing, their orbital periods were so extraordinarily long that some examples could take as many as 30 million years to complete just one single orbit around the Sunday. Even more curiously, these comets were observed to arrive from all different directions in space and had various, often highly tilted, orbital inclinations. It was a cosmic mystery of the grandest scale. However, Oort noticed a few crucial things that all of these long-period comets had in common. Their orbital paths clearly indicated that these comets were not coming from far out in truly interstellar space. Their origins had to be much closer to home, though, as we will explain, not too close to home. So, if these long-period comets were not originating from the Kuiper belt, which produces short-period comets, and were not coming from vast interstellar distances, where exactly were they coming from? Oort discovered a peculiar similarity among the orbital characteristics of all these comets, a similarity that might provide the key answer to the question: the point in any comet's orbit where it is the most distant from the Sun is called the aphelion. Oort noticed that all of the long-period comets observed seemed to have an aphelion that was tightly grouped around a certain distance, approximately 7.5 trillion kilometers from the Sunday. That's right, trillion with a T. As you can see, when we discuss the immense distances involved in this area of the solar system, our typical units of measurement, like kilometers, quickly become too cumbersome. So, instead of using kilometers, we will switch back to astronomical units, or AU. One astronomical unit is defined as the distance between the Earth and the Sun, which is about 150 million kilometers. Therefore, Earth is 1 AU. From the Sunday, the aphelion grouping that Oort noticed where the long-period comets reached their farthest orbital distance from the Sun clustered around 50,000 astronomical units. To help picture the sheer scale of the orbits of these long-period comets, recall that the outermost recognized planet in our solar system, Neptune, orbits at around 30 AU from the Sun, or about 4.5 billion kilometers. The main region of the Kuiper belt extends from Neptune's orbit at 30 AU out to around 50 AU. But even the furthest extension, the scattered disk, only continues to around 1000 AU. It was with these key findings that the comets did not originate from far out in interstellar space, that their orbital distances tightly clustered around 50,000 AU, and the fact that they arrived from any direction and orbital inclination that Oort finally theorized a special spherical swarm of icy debris that he believed to be the necessary origin of all long-period comets. In the years since 1950, mathematical models have shown strong agreement with the Oort cloud theory. Astronomers have further theorized various mechanisms by which the Oort cloud came to be in its current, distant state. The leading idea suggests that the Oort cloud formed from ancient debris, the same rocky and icy leftovers from when our planets formed 4.6 billion years ago. After the planets coalesced, the surrounding area was still rich with these smaller leftover chunks of material, known as planetesimals. The immense gravity from these early massive planets then dynamically scattered this leftover material in every conceivable direction. Some material was violently flung out of the solar system entirely, but a significant portion was sent into seemingly random, highly eccentric orbits around the Sunday. These scattered planetesimals were given eccentric enough orbits that they were then influenced by weak gravitational forces outside of our solar system, while still remaining permanently captured in the Sun's powerful gravitational field. It is believed that this complex scattering process is precisely how these billions, or even trillions, of ancient icy chunks came to be part of the distant Oort cloud. We think that just as gravitational perturbations can force Kuiper belt objects out of place, creating short-period comets, similar forces are what send Oort cloud objects into highly elliptical, falling orbits toward the Sun, thereby creating the long-period comets we observe. These perturbations could be caused by nearby passing stars, large molecular clouds, or even the weak yet constant tidal forces exerted by the vast Milky Way galaxy itself. In fact, about 70,000 years ago, a star named Scholz's star gained the title of the star that came closest to our solar system. That star actually grazed the very outer region of the Oort cloud, almost certainly sending a fresh wave of comets inward toward the Sunday. Luckily for our solar system, the low-mass Scholz's star did not cause any catastrophic gravitational disruptions to the Oort cloud or to the planets during its close passage. Scholz's star is actually a low-mass binary system, meaning it is composed of a small red dwarf star and an even smaller brown dwarf companion. This distinction is crucial. A red dwarf is a true star, fusing hydrogen in its core, although very slowly. A brown dwarf, however, is a failed star. It is too massive to be considered a planet, yet too small to sustain nuclear fusion. Even at a much closer distance to the Oort cloud 10 millennia ago, a distance estimated to be around 52,000 astronomical units, the combined gravitational influence of this binary star system was significantly weaker than the powerful central pull of our own, much more massive Sunday. However, while the majority of objects within the cloud experienced little to no effect during the low-mass star's brief close encounter with the edge of the Oort cloud, detailed numerical simulations published in 2018 concluded that Scholz's star is indeed believed to have nudged at least some objects out of their stable, distant orbits. This subtle but effective gravitational influence likely created new long-period comets and certainly altered the existing trajectories of others. This event serves as a concrete example of the theoretical mechanism that constantly replenishes the stream of comets arriving in the inner solar system. The Sun has been orbiting the center of the Milky Way galaxy for over 4 billion years. And that immense span of time has offered plenty of opportunities for other, much closer encounters with passing stars in the distant past. Could these numerous past stellar interactions have been so powerful that they actually prevented the Oort cloud from ever stabilizing and forming in the first place? Our current models suggest no. The overall stability of the cloud is greater than the transient disruption caused by passing stars. However, it is highly likely that Oort cloud material could be regularly exchanged with passing stars over eons, with our Sun gravitationally capturing some icy debris from other systems, and in turn, losing some of its own. More recent and sophisticated numerical simulations have strongly suggested that Oort clouds could exist around other star systems too. In fact, capturing material from nearby star-forming clusters might even be a necessary step in the final assembly of our own Oort cloud. Our Oort cloud may also have a far more complex structure than originally thought, possessing both an inner region and an outer region, each with its own distinct shape and likely different formation history. Some scientists propose that the inner region, sometimes called the Hills cloud, may be more flattened and disk-like, resembling the geometry of the Kuiper belt. This inner disk is thought to be more strongly bound to the Sun and less easily disturbed by passing stars. In contrast, the outer region is suggested to form the true spherical shell that is most widely associated with the classical Oort cloud theory. Altogether, the innermost edge of this proposed two-region Oort cloud may begin approximately 2,000 astronomical units from the Sun at its closest point. From there, the far edge could stretch all the way out into interstellar space, potentially reaching as far as 100,000 astronomical units from the center of our solar system. This means the complete Oort cloud could physically extend more than 1.5 light-years across. For context, this distance is approximately 1/4 of the distance to the nearest known star, Proxima Centauri. To fully put this immense, almost incomprehensible scale into perspective, consider the famous Voyager 2 spacecraft for a moment. As of the time of this video, Voyager 2 has traveled to a distance of about 139 astronomical units from the Sun since its launch from Earth, which is defined as 1 AU in August of 1977. That average rate of travel is about 3.3 AU per year, or roughly 56,000 kilometers per hour, which is over 34,000 miles per hour. It is currently the second farthest human-made object in space, just behind its twin probe, Voyager 1. In August 2007, Voyager 2 passed beyond the boundary of the termination shock, and then the heliosphere, the protective magnetic bubble created by the Sunday. This magnetic influence extends out beyond all the planets and is 3 times further than the distance to Pluto. Outside of the heliosphere, the Sun's constant flow of charged particles, called the solar wind, is finally impeded and pushed back by the interstellar medium, the gas and plasma found between star systems. Then, in November 2018, Voyager 2 finally crossed the final layer of solar turbulence known as the heliosheath and continued its journey into true interstellar space. Despite having passed beyond the immense heliosphere and well past the main Kuiper belt region, Voyager 2 would still need to travel for another 300 years or so just to reach the absolute innermost edge of the theorized Oort cloud. That is how staggering the distance truly is. Even at speeds of tens of thousands of kilometers per hour, and to fly completely through the full expanse of the Oort cloud, from inner edge to outer boundary, that journey could take another 30,000 years. Even traveling at an astonishing speed of 56,000 kilometers per hour, it still takes all that time just to travel around 1/2 of a light year. If you have ever wondered why practical interstellar or intergalactic space travel is incredibly difficult, keep in mind that our nearest stellar neighbor, Proxima Centauri, is still around 4.25 light-years away from us. Any realistic interstellar mission would need propulsion systems that are orders of magnitude faster than current technology allows. Despite the mounting evidence and the strong theoretical basis, some scientists still question the definitive existence of the Oort cloud, mainly because we are entirely unable to directly observe it. Another key argument that has been raised is the possibility that long-period comets might actually originate from other places, such as true interstellar space. In fact, the first ever definitive observation of an interstellar comet, one that had clear origins from outside our Sun's gravitational influence, was made in 2019 by the amateur astronomer Gennady Borisov. These interstellar objects are identified by their hyperbolic orbits, meaning their path is so fast that it curves through our solar system but is not gravitationally bound to the Sun, confirming their outside origin. Professional astronomers quickly joined in to collect comprehensive data on Comet Borisov, named after its first observer. They discovered an unusual composition, a significantly higher concentration of carbon monoxide than the average comet originating from our own solar system. This finding strongly suggests that this comet may have formed in the presence of a red dwarf, a fundamentally different type of star than our Sunday. The carbon monoxide would have required a much colder formation environment than was available in our primordial solar system, and yet the vast majority of astronomers agree that the Oort cloud is truly out there, despite the fact that we have never physically laid eyes on it. Plenty of indirect observations, such as the clustered aphelion distances of long-period comets and sophisticated mathematical models that trace the scattering history of planetesimals, show powerful support for the theory, and the accumulating evidence continues to make the case stronger. But why, exactly, have we never been able to see the Oort cloud? The fundamental challenge comes down to size and light. Think about the scale. A single piece of Oort cloud debris is roughly the size of a single mountain on Earth. Let's consider Mount Everest, which is around 9 kilometers tall. Now, recall that the Oort cloud's innermost boundary begins somewhere around 2,000 astronomical units, or roughly 300 billion kilometers from the Sunday. The distance from the Sun to the nearest piece of Oort cloud debris is about 33 million times the physical size of that debris. This truly is the challenge of looking for a needle in the cosmic haystack. But even more crucial than size is the factor of light. Stars and distant galaxies actively emit their own light, making them visible across vast gulfs of space. Planets are relatively close to the Sun, so they are able to reflect the Sun's light and are therefore visible. Likewise, the asteroid belt and even the relatively close Kuiper belt are near enough to the Sun that we can use powerful telescopes to directly observe the tiny amounts of light their debris reflects. But outside of the heliosphere, the Oort cloud is simply too far and too dark for our current telescopes to catch a glimpse. The sunlight that reaches that distance is too weak, and the light that is reflected is too faint to be detected back on Earth. This lack of reflected light is the single greatest observational hurdle. Despite the Oort cloud's gargantuan footprint and its pivotal inferred role in shaping our understanding of the origin of many long-period comets, for now, we can still only infer its existence through mathematical models and indirect observation. But do not let our current inability to make direct observations discourage you from following the scientific evidence. We can recall other times in history when scientists put forth monumental theories despite a lack of direct photographic observation. For example, in the 16th and 17th centuries, respectively, Copernicus and Galileo put forth the theory that the planets orbited around the Sunday. This groundbreaking idea directly contradicted the widely held belief at the time that the Earth was the center of the solar universe. Their theory of a heliocentric solar system was not based on direct observation in the modern sense, but rather on the consistent patterns and indirect observation of the planet's orbital mechanics. As we now know, that theory turned out to be spot on. completely reshaping humanity's place in the cosmos. That is the remarkable thing about science and the relentless pursuit of knowledge. There is always more to learn and uncover. The farther we travel through time, the better our understanding of the solar system will inevitably get. We are constantly developing new tools, like advanced infrared telescopes and innovative orbital surveys that push the boundaries of detection. Who knows? Maybe in 100 years, future astronomers will have finally found a way to conclusively prove the existence of the Oort cloud once and for all, perhaps by detecting the subtle gravitational influence of the inner Hills cloud, or through the direct observation of a very large object located within its bounds. Or perhaps they will have found an entirely new and different explanation for the existence of long-period comets. Until that day comes, the Oort cloud remains one of astronomy's most compelling and elusive enigmas. It is time to return our focus back toward the inner solar system, where the activity is much more fast-paced. There are literally millions of asteroids in our solar system, and surprisingly, there are also many different types, each with its own unique composition, reflecting the varied conditions under which they formed. They are not just found confined within the asteroid belt, but they are, in reality, darting all around our solar system, sometimes in very unexpected places. We return now to the inner solar system, where objects move with much greater speed and in orbits much closer to the massive energy of the Sunday. There are literally millions of asteroids in our solar system, yet these objects are far from uniform. Surprisingly, there are many different types, each with its own unique composition, reflecting the varied conditions and temperatures under which they originally formed. These objects are not merely confined within the familiar asteroid belt between Mars and Jupiter. In reality, they are darting all around our solar system, sometimes appearing in very unexpected places. But what exactly is an asteroid? The term is an astronomical classification for a minor planet or a small solar system body. More specifically, a minor planet is an umbrella term for a small body orbiting the Sun that is not outgassing, meaning it is not actively releasing gas or material from its surface to form a visible cloud. Asteroids are generally solid bodies, composed mainly of rocky or metallic material. However, they may still contain volatile compounds, such as water ice or frozen gases protected underneath the surface crust, shielded from intense sunlight. This leads directly to the question of the difference between an asteroid and a comet. Comets are distinguished precisely because they have these same volatile materials positioned much closer to or on their surface. When a comet is heated by solar radiation as it nears the Sun, these frozen materials instantly turn into gas or sublimate, producing a glowing cloud called a coma and the characteristic tails that we observe from Earth. This distinction between asteroids and comets has been a bedrock of astronomical classification for over a century. However, modern observations have shown that the lines between these categories are far more blurred than previously thought. The level of visible activity from a small body is largely dependent upon one key factor: its distance from the Sunday. For instance, objects that exist far beyond the orbits of Neptune are effectively inert or dormant all year round, even if they are made almost entirely of ice. However, if those same icy objects were somehow pulled into an orbit that brought them close to the Sun, they would immediately begin to sublimate and would transform into comets. Furthermore, we have discovered objects that appear rocky like an asteroid, but temporarily show cometary activity, leading to a new classification: active asteroids or main belt comets. Therefore, while watching this exploration, keep in mind that the classification often describes the current state of the object, not its ultimate composition. We will focus exclusively on asteroids that have orbits primarily within the inner solar system, generally between the Sun and Jupiter. Not all asteroids are created equal. Beyond the obvious differences in size, which range from mere dust particles all the way up to the biggest known asteroid, Ceres, which is almost 1,000 kilometers in diameter, asteroids are also scientifically classified based upon their spectrum or color. This spectral analysis reveals how the object reflects sunlight, which in turn strongly indicates what the asteroid is chemically made of. The vast majority of the asteroids we've discovered can be sorted into three major categories based on their color and how they reflect sunlight, a technique called spectral classification. First, there's the C group, or carbonaceous asteroids. These are the darkest, making up about 75% of the entire known asteroid population. They are chemically rich in carbon, water, and other volatile materials, meaning they haven't changed much since the solar system was born. They act like frozen time capsules of the raw materials that originally formed the planets, believed to have condensed in the cooler, outer parts of the early solar system. Their composition is similar to carbon-rich chondrite meteorites that sometimes land on Earth. The second and third groups are brighter and tell a different story of heating and change. S-type asteroids are stony or siliceous, meaning they are made mainly of silicate rock, like the rocks found on Earth, mixed with metals such as iron and magnesium. These asteroids are most common in the inner part of the asteroid belt and are thought to have undergone some differentiation. This means they were heated enough in the distant past for their heavy metallic materials to sink inward, leaving the lighter, rocky crust on the surface. Finally, the M-type, or metallic asteroids, are the brightest of all. They are relatively rare and are concentrated in the middle region of the belt. Scientists believe these shiny objects are essentially the exposed cores of much larger ancient objects that were shattered by catastrophic impacts, stripping away their original rocky outer layers and leaving behind the pure nickel-iron metal center. There are other, less common types as well, but they are generally variations or subgroups of these three core categories. Understanding these classifications is fundamental to interpreting the history and movement of these small worlds. Now, let's explore some of the most compelling asteroids discovered so far, beginning with the outliers. Number 10. 2005 volts X3, the Extreme Traveler. The object known as 2005 VX3 holds the record as the minor planet with the largest aphelion, the point in its orbit farthest from the Sun that we know of. At its closest approach to the Sun, called perihelion, it is only 4.1 astronomical units away, which is just inside the orbit of Jupiter. But when it swings to its farthest point, it achieves an estimated heliocentric distance of a massive 3,000 astronomical units from the Sunday. Because of this monumental difference between its closest and farthest points, 2005 VX3 is estimated to have the largest orbital eccentricity, E number, of any known minor planet. Eccentricity is a measure of how far an orbit deviates from a perfect circle. A perfectly circular orbit has an eccentricity of 0, while an object escaping the Sun's gravity would have an eccentricity of 1 or greater. 2005 VX3 has an eccentricity near 0.999, making its path highly elongated. The last time this object was observed was in January 2006, when it reached its closest point to the Sunday. Based on its calculated path, it will likely not be seen again for another 30 to 40,000 years. Scientists believe this object could be a dormant comet that is currently not showing any visible outgassing. It may have made closer approaches to the Sun in the past, which would have removed most of its surface volatile, icy materials. This explains why it currently has no visible tail or coma, and why we classify it as an asteroid instead of a comet. It is estimated to be quite small, only about 7 kilometers in diameter. Its extreme orbit makes it a powerful example of the transition objects that challenge our definitions. Number 9. 99942 Apophis, the near miss. 99,942 Apophis is a near-Earth asteroid that caused significant concern when it was first discovered. In December 2004, initial observations indicated a calculated probability of about 2.7% that it would strike Earth on April 13, 2029. This caused quite a stir in both the scientific community and the media. Fortunately, as additional observations were made and refined, the asteroid's predicted orbit was improved dramatically, which successfully eliminated the chance of a direct collision in 2029. However, a serious possibility remained. During this very close flyby in 2029, Apophis could pass through what is called a gravitational keyhole. A keyhole is an incredibly small region in space, no more than about 800 meters wide, where Earth's gravity would precisely alter Apophis's orbit, just enough to put it on a dangerous impact scenario, exactly 7 years later, in 2036. This possibility kept Apophis at level 1 on the Torino impact hazard scale for an extended period. The Torino scale is an internationally recognized method for categorizing the impact risk of near-Earth objects, with levels ranging from 0, no hazard, to 10, certain global catastrophe. Apophis did, in fact, set the record for the highest rating ever achieved on the scale, briefly reaching level 4 at one point, which signifies a concern warranting attention. The risk was downgraded in August 2006, when the probability that Apophis would pass through the keyhole was determined to be extremely small. By now, the possibility of a 2036 collision has been effectively ruled out by further analysis. Had Apophis hit Earth, the estimated kinetic energy released would have been equivalent to about 750 megatons of TNT. To put that power in perspective, that is approximately 13 times more powerful than the largest hydrogen bomb ever exploded by humanity. Such an impact would cause devastating regional damage, though it would not be a global extinction event. Apophis is a stony S-type asteroid. The most recent observation in 2013 estimated its size to be about 325 meters across. Interestingly, an asteroid the size of Apophis is expected to strike Earth about every 80,000 years on average. The study of Apophis greatly advanced planetary defense research. Number 8. 25143 Itokawa, the rubble pile. 25,143 Itokawa is a Mars-crossing asteroid, meaning its orbit takes it inside the orbit of Mars. This small body gained fame by being the first asteroid ever targeted by a sample return mission, successfully accomplished by the Japanese space probe Hayabusa. Itokawa holds another record. It is the smallest asteroid ever to be thoroughly photographed by a spacecraft, measuring only about 500 meters across at its longest point. It is classified as an S-type asteroid, but its unique characteristics suggest it may be a contact binary, two separate bodies that merge gently over time. Crucially, the surface of Itokawa shows very little in the way of sharp impact craters. Instead, it is almost entirely covered in large boulders and smaller fragments, leading the mission team to describe it as a giant rubble pile. Scientists estimated its average density to be only about 1.8 grams per cubic centimeter. For context, solid Earth rock typically has a density of around 3 grams per cubic centimeter. The low density of Itokawa confirms that it cannot possibly be a single, solid piece of rock. It is instead a loosely bound collection of fragments, gravel, and boulders that have gravitationally aggregated over time with large empty spaces or voids between the pieces. This rubble pile structure created a navigational challenge. Itokawa's gravity was so weak due to its small size and low density that it was not strong enough to enable the Hayabusa space probe to enter a stable orbit around it. Instead, the engineers employed an ingenious technique. They essentially parked the space probe next to the asteroid, allowing it to orbit the Sun alongside Itokawa. In 2010, the probe successfully landed on the asteroid's surface for a quick touch-and-go maneuver and successfully returned minute dust samples from the surface back to Earth, proving that planetary science can be done even on the smallest, most gravitationally fragile worlds. Number 7. Pallas, the highly tilted giant. Pallas holds the distinction of being the second asteroid ever discovered, found just 1 year after Ceres. When astronomers were searching for Ceres again following its initial discovery in the early 1800s, they accidentally stumbled upon Pallas, which happened to be coincidentally nearby at the time. When Pallas was found, it was immediately counted as a planet, following the practice for other major asteroids in the early 19th century. However, the subsequent discovery of many more asteroids after 1845 ultimately led to their collective reclassification as minor planets. Pallas remains one of the most massive asteroids in the solar system. It is estimated to comprise approximately 7% of the total mass of the entire asteroid belt. With a mean diameter of 544 kilometers, Pallas is structurally slightly larger than Vesta. However, it is between 10 to 30% less massive than Vesta, placing it third among the known asteroids in terms of total mass. Pallas is classified as a C-group asteroid, meaning it has a very low albedo or reflectivity. Its dark, carbon-rich surface reflects only about 4% of the light that falls upon it. This low reflectivity is comparable to the darkness of fresh asphalt. At its brightest point in its orbit, Pallas may be visible with simple binoculars, but it is not visible to the naked eye. The most defining feature of Pallas is its highly unusual orbit. It is inclined at a steep 34.8 degrees relative to the main plane of the solar system, where the major planets orbit. This extreme tilt means that Pallas is virtually inaccessible to any spacecraft that might want to investigate its surface closely. Any probe launched to Pallas would require an enormous amount of fuel and time for complex, high-energy maneuvers just to match Pallas's highly tilted orbital plane, making a rendezvous mission practically unfeasible with current technology. Number 6. 1019 Chariklo, the ringed centaur. The object known as 1019, Chariklo technically should not appear on this list, but its astonishing discovery makes it impossible to ignore. The reason it falls outside the standard asteroid definition is that it is classified as a centaur. A centaur is a class of minor planet that orbits within the outer region of the solar system, specifically situated between the orbits of the gas giants, in this case, between Saturn and Uranus. Chariklo is the largest known centaur, measuring over 300 kilometers in diameter. The remarkable feature that secures its place on this list is its ring system. Much like the complex icy rings encircling Saturn, but on a dramatically smaller scale. In 2013, astronomers discovered that Chariklo possesses two distinct rings, one estimated to be 7 kilometers wide and the other about 3 kilometers wide, separated by a gap of about 9 kilometers. This makes Chariklo the smallest known object in the solar system to ever have a ring system. In fact, because Chariklo is so small and its gravitational pull is so weak, its rings should not be stable at all. The physics dictates that such fragile structures should quickly disperse. This implies that either the rings are actively being maintained by small, unseen shepherd moons orbiting nearby, which use their gravity to keep the particles in place, or the rings are relatively young and will slowly erode and dissipate over the next few million years. The existence of rings on such a tiny, icy body has profoundly challenged our understanding of how these complex systems form and persist. Centaurs themselves are considered unstable objects. Their orbits are constantly being perturbed by the giant planets, meaning Chariklo will eventually be ejected from the solar system or thrown into the inner system, where it will likely become a large, short-lived comet. Number 5. Lutetia, the composition enigma. Lutetia is a large, unique M-type asteroid found within the main asteroid belt. It measures about 100 kilometers in diameter and rotates in a retrograde direction, meaning it spins backward relative to the orbits of the planets. Lutetia is distinguished by possessing one of the greatest densities of any asteroid ever observed. Its average density is estimated to be about 3.4 grams per cubic centimeter. This high density strongly suggests that it must be made of metal-rich rock. However, the asteroid presents a bizarre contradiction. There is surprisingly little clear evidence of pure metal on its surface, and its color spectrum visually resembles more of a C-group carbonaceous asteroid. Despite the surface appearance, the calculated high density proves that it must indeed contain significant amounts of heavy metals deep within its structure. It is speculated that Lutetia's metal-rich core is surrounded by a thick layer, perhaps 3 kilometers deep, of dust and loose rock called regolith. This theory is supported by the fact that impact craters on the surface have strangely softened outlines, suggesting the underlying bedrock is covered by a substantial cushioning layer of loose material. Lutetia has an irregular shape and is heavily scarred, with the largest impact crater reaching 45 kilometers in diameter. The European Space Agency's Rosetta probe performed a close flyby of Lutetia in 2010, collecting valuable data on its mass, shape, and unusual composition. Number 4. 433 Eros. The Resource Prospect. 433 Eros is an S-type asteroid that is approximately 34 kilometers long. It holds the distinction of being the second largest near-Earth asteroid, surpassed only by 1036 Ganymede. Eros is classified as a Mars-crossing asteroid and was the first asteroid known to occupy such an orbit. The orbits of Mars-crossing objects are inherently unstable and can typically remain there for only a few 100 million years before being perturbed by Mars's gravity. Eros's orbit is dynamically unstable, and scientists have calculated that it may evolve into an Earth crosser in as short an interval as 2 million years. Even more concerning is that it apparently has roughly a 50% chance of doing so within the next 100 million years. This change would turn Eros into a potential Earth impactor, comparable in size to the massive body that created the Chicxulub crater, the impact event that led to the extinction of the dinosaurs, releasing the destructive energy equivalent of a 100 teraton weapon. The NASA Near Shoemaker probe visited Eros in 1998 and 2000. The mission culminated in a spectacular finish. The probe was commanded to attempt a surface landing, a maneuver for which it was never originally designed. Despite this, Near Shoemaker successfully completed its mission by physically landing on the surface of Eros in 2001, becoming the first spacecraft to soft land on an asteroid. If the sheer geological and historical significance of Eros is not enough, the data collected suggested that it contains an estimated 20 billion tons of valuable rare metals, such as gold and platinum. This immense concentration of resources makes Eros a prime target for future asteroid mining and resource exploitation concepts. Number 3. 243 Ida. The discovery of an asteroid. Moon. 243 Ida is a stony S-type asteroid located within the main asteroid belt. In 1993, Ida was visited by the Galileo spacecraft while the probe was en route to its main mission orbiting Jupiter. Ida has an average diameter of 31.4 kilometers. It is irregularly shaped and elongated, appearing to be composed of 2 large segments that have connected together. Its surface is one of the most heavily cratered in the solar system, testifying to a long, violent history of impacts. Ida's average density is about 2.6 grams per cubic centimeter, which is fairly typical for a solid, rocky asteroid. Like all asteroids of this size, it has extremely weak gravity. The theoretical escape velocity, the speed needed to escape its gravity, is only about 20 meters per second. This means that if a person could jump away from the surface faster than 20 meters per second, they would escape the asteroid's gravity altogether. Conversely, with a slight jump, you could theoretically leap from one end of the 30-kilometer-long asteroid to the other in a single bound. But what makes Ida most fascinating is the discovery of its tiny moon, Dactyl. Dactyl measures only 1.4 kilometers in diameter, making it about 1/120th the size of Ida itself. The moon was named after the Dactyls, mythical creatures said to inhabit Mount Ida. In Greek mythology, Dactyl and Ida share many characteristics, implying they originated from the same parent body. While we now know of other asteroids that possess moons, Ida is the only one for which we have high-definition imagery of both the main body and its satellite, allowing for detailed study of their interaction. Number 2. 4. Vesta, the protoplanet, remnant. Vesta is the second most massive object in the entire asteroid belt, following only the dwarf planet Ceres. It has a mean diameter of 525 kilometers. Vesta is classified as the last remaining rocky protoplanet, a planetary embryo that never fully matured. This status means that Vesta has a differentiated interior, possessing distinct layers similar to those formed in the terrestrial planets, including a small metallic core. The immense collisions that Vesta endured billions of years ago, which left the two enormous craters occupying much of Vesta's southern hemisphere, ejected numerous fragments into space. Debris from these impacts has since fallen to Earth as howardite, eucrit, diogenite, head meteorites. These HED meteorites are a valuable source of information about Vesta's interior composition, effectively bringing samples to us without the need for emission. Other fragments remained in similar orbits to Vesta. There are so many of them that, along with Vesta itself, they have been grouped into their own class of asteroid, the V-type asteroids. Vesta is the brightest asteroid visible from Earth. It also contains one of the solar system's most dramatic geological features, the central peak of the largest crater, Rhea Silvia, which rises about 22 kilometers high, making it one of the tallest mountains in the entire solar system. NASA's Dawn spacecraft entered orbit around Vesta in 2011 for a highly successful one-year exploration, collecting a vast amount of data that researchers are still sifting through years later, providing unparalleled insight into the formation of rocky worlds. Number 1. Ceres, the dwarf planet in the belt. Finally, we arrive at Ceres, the only dwarf planet located within the asteroid belt. Ceres was counted as a planet for many years due to its massive size, which spans about 960 kilometers in diameter. It is composed of both rock and ice, and is estimated to make up about 1/3 of the mass of the entire asteroid belt. Ceres is so large that it is the only asteroid rounded by its own gravity, a key requirement for dwarf planet status. Even so, in planetary terms, it remains quite small. Our moon, in comparison, is enormous. Scientists believe that Ceres possesses a rocky core, a massive icy mantle, and may even harbor a remnant internal ocean of liquid water beneath a layer of ice. It is classified as a carbonaceous, C-type asteroid, meaning its surface is likely a mixture of water, ice, carbonates, and clay. The Dawn spacecraft, after concluding its mission at Vesta, successfully entered orbit around Ceres in 2015. One of its most surprising findings was the detection of emissions of water vapor escaping from Ceres. This was highly unexpected, as asteroids in the asteroid belt do not typically give off vapor. That kind of activity is usually reserved for comets. This finding confirmed that Ceres is a dynamically active world, blurring the traditional lines between asteroids and comets and solidifying its position as one of the most fascinating small worlds in our solar system. The data returned by the Dawn mission during its orbit around Ceres provided the final, compelling evidence of the dynamic nature of these small worlds, culminating in the mystery of the bright spots. Initial low-resolution images from the spacecraft showed one or two highly reflective areas inside a prominent crater, immediately sparking global scientific excitement. These spots were theorized to be highly reflective materials, most likely containing concentrated salts or water ice that had recently been exposed. As NASA released progressively higher resolution imagery, it became clear that instead of just one or two luminous patches, there were actually several distinct spots clustered within the crater floor. This complexity solidified the understanding that Ceres is not merely a static, ancient rock, but an active body undergoing ongoing geological processes driven by its internal composition. This finding on Ceres serves as a perfect final point to connect all the small, intriguing worlds we have explored, from the inner asteroid belt to the far reaches of the Oort cloud. Our journey began with Vesta, the rugged, oddly shaped protoplanet remnant. Vesta taught us about the violent, high-energy collisions that shaped the early solar system. Its differentiated interior, with a rocky mantle and metallic core, proves that it started the journey toward becoming a full planet. The presence of Vesta fragments on Earth, delivered as head meteorites, underscores the deep interconnectedness of the solar system, providing us with direct samples of a planetary embryo without the need for a sample return mission. Vesta's story is one of formation, heating, and subsequent cooling, a snapshot of arrested development preserved by the disruptive gravity of Jupiter. The mission then led us to Ceres, the only dwarf planet in the asteroid belt. Ceres's massive water ice content, its differentiated structure, and the evidence of past liquid flow and potential internal ocean hinted at a world fundamentally different from Vesta. The bright spots, now understood to be deposits of salt left behind by sublimating, salt-rich water that erupted from cryovolcanoes, confirm that Ceres is experiencing cryovolcanic activity. This process suggests that heat, possibly generated by the decay of radioactive materials or by gravitational stress, is capable of melting subsurface ice, allowing briny water to flow and renew the surface. Even today, this evidence of geological activity on a small, icy world has profound implications for understanding the potential for subsurface habitability in the outer solar system. Moving beyond the asteroid belt, we ventured into the dark, icy expanse of the Kuiper Belt. This region, home to Pluto and the bizarre contact binary Arrokoth, revealed the conditions of the cold, early solar system. The gentle, low-speed merger that formed Arakoth provided conclusive proof for the theory of local cloud collapse, the idea that planet building blocks formed through quiet aggregation, not violent, high-speed collisions. The Kuiper Belt is the reservoir of short-period comets and a fundamental time capsule, showing us the icy, volatile-rich material that was scattered outwards during the planetary migration era. Our understanding then stretched to the theoretical boundary of the solar system, the Oort cloud. This immense, spherical shell of icy debris, though never directly observed, is mathematically necessary to explain the existence and random arrival directions of long-period comets. The Oort cloud's origin, the forceful scattering of leftover planetesimals by the giant planets and its vast scale, extending tens of thousands of astronomical units, illustrate the Sun's tenuous hold on material at the very limits of its gravitational domain. The cloud's constant state of agitation, caused by passing stars like Schultz's star and the tidal forces of the Milky Way, ensures a continuous, though sporadic supply of new comets falling toward the inner system. Finally, we explored the incredible diversity of the small objects themselves, categorizing them into the three main types based on their composition: the primitive, carbon-rich, C-type asteroids, the rocky, differentiated S-type asteroids, and the metallic cores of shattered bodies, the M-type asteroids. We highlighted objects like Pallas, with its highly tilted orbit, the unexpected ringed centaur Chariklo, the low-density rubble pile Itokawa, and the resource-rich, potential Earth impactor Eros. These unique examples demonstrate that the term asteroid encompasses a vast range of origins, structures, and histories, from solid metallic cores to loosely bound piles of gravel and ice. The common thread uniting all these small worlds, from the active cryovolcanoes of Ceres to the gravitational keyhole threat of Apophis and the distant unseen icebergs of the Oort cloud, is the continuous, dynamic process of the solar system. These bodies, once dismissed as mere space rubble, are now recognized as the original building blocks and the most sensitive indicators of planetary migration, gravitational stability, and even the potential delivery of water and organic compounds to early Earth. Their study is not just about cataloging rocks. It is about reconstructing the complex, violent, and fascinating history of our cosmic home. The observation of the multiple, bright, salty spots on Ceres confirms that these small worlds are still very much alive, waiting to yield their secrets to future missions and better technology.